Marie Curie's laboratory notebooks are still radioactively contaminated. More than a century after she handled radium in rooms with almost no protection, the invisible material remains caught in the paper fibers. That detail often turns Curie into a neat little cautionary tale. Brilliant scientist discovers radiation. Radiation kills brilliant scientist. Science gives her 2 Nobel Prizes, and then sends an invoice. The real story is more complicated. Marie Curie paid for her discoveries in exhausting labor, poverty, public humiliation, grief, and eventually, very probably, her health. But the same radiation that damaged human tissue could also reveal a bullet inside a wounded soldier, or destroy a tumor. Her life was not a simple warning against dangerous knowledge. It was the story of learning what nature could do before anyone understood the price of standing too close. She was born Maria Skłodowska in Warsaw in 1867, when the city was controlled by the Russian Empire. Polish language and culture were suppressed, and universities did not admit women. Maria studied through informal, underground courses, sometimes called the Flying University, because classes moved around to avoid the authorities. It was higher education with the added administrative inconvenience of possibly being raided. She and her older sister Bronisława made a practical agreement. Maria would work to support Bronisława through medical school in Paris. Later, Bronisława would help Maria study there. Maria spent years as a governess, teaching other people's children while educating herself at night. In 1891, aged 24, she finally arrived in Paris. She adopted the French form of her name, Marie, and enrolled at the Sorbonne. Money was scarce. Her rooms were cold, her meals were thin, and she sometimes became ill from hunger and overwork. Yet she finished first in her physics degree and second in mathematics. Paris had given her access to a university. It had not included central heating in the arrangement. In 1894, she met Pierre Curie, a physicist known for precise experimental work. They married the following year. Their partnership became unusually close, both personally and scientifically. But the question that changed their lives began as Marie's own doctoral research. In 1896, Henri Becquerel had discovered that uranium compounds emitted mysterious rays without needing sunlight or an outside energy source. Marie chose to measure this phenomenon systematically. Using a sensitive electrometer, she measured how the rays made air conduct electricity. Her crucial insight was that the strength of the radiation depended on how much uranium was present, not on the chemical form containing it. The energy seemed to come from inside the atom itself. At the time, atoms were generally treated as permanent little building blocks. Marie's measurements suggested the blocks were doing something behind everyone's back. Then she tested pitchblende, a dark uranium ore. It was more radioactive than pure uranium. That made no sense unless the ore contained another substance, present in tiny quantities but far more active. If badly drawn science and remarkably determined people suit you, subscribe before we return to the boiling vat. Pierre set aside his own research and joined the search. Together, they crushed, dissolved, filtered, heated, and separated pitchblende into chemical fractions. After each separation, they measured which fraction remained most radioactive. Radiation became their trail of breadcrumbs. Except the breadcrumbs were invisible and quietly damaging the furniture. In July 1898, they announced evidence for a new element. Marie named it Polonium after Poland, a country that did not then exist as an independent state. The name was scientific and political at once. In December, they announced another element, radium. Announcing an element was not enough. They had to separate enough material to prove what it was. The problem was concentration. Radium was buried among ordinary elements in absurdly small amounts. Their working space was an abandoned shed once used for medical dissections. It leaked when it rained and became brutally hot when Marie processed mineral in heavy iron vessels. She stirred boiling material with a long rod, reduced solutions, produced crystals, dissolved them, and repeated the process. It was part chemistry laboratory, part laundry, and part medieval soup operation. Industrial partners helped process larger quantities, so the familiar image of Marie doing every step entirely alone is too romantic. Even with that assistance, she spent more than 3 years separating material from tons of pitchblende residue. The result was roughly 1/10 of a gram of radium chloride, pure enough to measure and establish radium as a new element. The deeper discovery was not merely that 2 new boxes could be added to the periodic table. Curie helped show that radioactivity was an atomic property. Certain unstable atoms change spontaneously, releasing energy and particles as they become other atoms. This eventually forced scientists to abandon the idea that atoms were indivisible and unchanging. In 1903, Marie completed her doctorate. That year, the Nobel Prize in Physics was planned around Becquerel and Pierre. Marie's contribution was nearly omitted. After the Swedish mathematician Gösta Mittag-Leffler alerted Pierre, he insisted that excluding her would misrepresent the work. The final prize went to Becquerel, Pierre, and Marie, making her the first woman to win a Nobel Prize. Recognition did not produce a comfortable laboratory immediately. It did produce reporters, visitors, requests, and the peculiar experience of becoming famous for work she no longer had enough peace to continue. Then, in April 1906, Pierre was killed after falling beneath a horse-drawn wagon on a wet Paris street. His death was sudden and devastating. Marie had lost her husband, closest collaborator, and the person who had consistently treated her as a scientific equal. She accepted his position at the Sorbonne and became the university's first woman professor. Her first lecture drew a large crowd expecting a grand tribute. Instead, she reportedly began where Pierre's previous lecture had ended. Grief would have to wait. There was material to cover. In 1911, she received a second Nobel Prize, this time in chemistry, for the discovery of polonium and radium, the isolation of radium, and her study of its compounds. She remains the only person to receive Nobel Prizes in 2 different scientific categories. The award arrived during a vicious press scandal over her relationship with the physicist Paul Langevin, who was separated from his wife but still married. Newspapers attacked Curie as a foreign intruder and portrayed her private life as a public emergency. She attended the Nobel ceremony anyway. Whatever anyone thought of her relationship, it had not altered the measurements. By then, radium had become both a serious medical tool and a commercial craze. Its ability to damage living cells suggested a way to attack tumors. It also appeared in dubious medicines and consumer products sold with more enthusiasm than evidence. Radiation was new, mysterious, and profitable, a combination that has rarely encouraged restraint. Curie understood that radiation could cause burns. Pierre had deliberately exposed his arm to radium and documented the resulting wound. But the long-term effects of repeated exposure were still poorly understood. Early researchers handled radioactive substances directly. Protection was inconsistent. Contamination spread across benches, instruments, clothes, and notebooks because nobody could see or smell it. When the First World War began in 1914, Curie found another use for invisible rays. Surgeons treating wounded soldiers often needed to locate bullets, shrapnel, and broken bones without blindly cutting into damaged tissue. X-rays could show them where to operate, but the machines were usually far from the front. Curie helped equip vehicles with X-ray apparatus and electrical generators. These mobile radiology stations became known as Petite Curies, or Little Curies. She learned to drive, study basic automobile maintenance, traveled to hospitals, and helped establish 20 mobile units and around 200 fixed installations. She also trained roughly 150 women as radiological assistants. Her teenage daughter Irene worked beside her. The machines were primitive and shielding was limited. Operators sometimes judged exposure by watching their own skin redden, which is a method modern workplace safety departments tend to discourage. The X-ray units helps doctors treat enormous numbers of wounded soldiers. They also added to Curie's exposure. X-rays and radium are not the same thing, but both produce ionizing radiation. This carries enough energy to damage molecules and cells. That damage can be directed against cancer or used in carefully controlled doses for imaging. With enough exposure, it can also injure healthy tissue and bone marrow. Curie continued working after the war, directing the Radium Institute and promoting medical research. In 1934, aged 66, she died from aplastic anemia, a failure of the bone marrow to produce enough blood cells. Her doctors connected the illness to long exposure to radiation, and that remains the most likely explanation. It is impossible to reconstruct exactly how much came from radium, X-ray equipment, or other sources across decades. Curie was not completely unaware of danger, but neither she nor her generation possessed today's understanding of dose, contamination, shielding, and cumulative risk. She worked during the awkward period when humanity knew radiation existed, knew it was useful, and was still discovering what it did to the person holding the tube. Her papers really are contaminated and require controlled preservation. The popular claim that her body remains dangerously radioactive is much less reliable. When her remains were transferred to the Pantheon in 1995, measurements found no danger to workers or the public. Marie Curie did pay for her discovery, but not because nature punishes curiosity. She paid because discovery often arrives before safety manuals, institutions, and common sense have caught up. She opened the atom and found light, medicine, danger, and an entirely new science inside. The notebooks remain behind, still carrying faint traces of the work. Not a curse, not a moral, just evidence that Marie Curie got there first.